Hello, everyone. How are you today? I hope everybody's doing pretty good. Thank you and welcome to this talk. Okay. Today, we're going to be reviewing a review, which it means that it is just a lot of different papers combined into one. Okay. So it's just a review, a summary of many works in this field. And today's title is Influence of Nanotechnology and the Role of Nanostructures in Biomimetics Studies and Their Potential Applications. Okay, let's get started. So, what's up for today? So, we're going to be talking about what is nanotechnology, nanoscience, material synthesis, spectroscopic, microscopic tools, and what is really biomimetics and how nanotechnology has influenced it. Let's get started. What is nanotechnology? Nanotechnology is just a measurement of matter from from 0 to 100 nanometers. 1 centimeter contains 10,000 nanometers. So centimeter is probably something like this. It contains about 1,000 nanometers. So if we look only at one molecule of water, that would be zero point 0.1. If we only look at one glucose, it would be 1 nanometer. But in 1 grain of glucose, there's a lot and thousands of um, this little of 1 nanometer glucose. Okay, so that is nanotechnology. It's just a measurement of at this scale. Okay, nanoscience is just really science using this scale to make materials or make something. Okay, at this molecular level. Spectroscopic and microscopic tools is just these are tools that we have developed that can help us see things or matter at this scale from 0 to 100 nanometers. Okay. And what is biomimetics and how nanotechnology has influenced it? Biomimetics is just it looks at nature and it gets inspiration from nature to make things. Okay. And nanotechnology, such as has developed tools such as spectroscopic tools, which are just microscopic tools. So we're able to see further inside and then get inspiration from nature at a molecular level, which would be in this level. Okay. So now for the introduction for this paper, we explain already what is biomimetics. It is the same as biomimicry, which is just mimicking nature. Whatever nature does, we want to do it. Okay. But nature uses natural models, processes, and different elements, different chemical elements, and they do it in a different way. Every animal does things in a different way. For example, Leonardo da Vinci, he really looked at how birds fly, and then he got inspiration from them. So that is just biomimicry. Uh, Now, biomimetics or biomimicry, we can look at a nanoscale. That's how nanotechnology has influenced it. We can look at a nanoscale. Not we're not just like Leonardo da Vinci, just looking at birds at which they're pretty big. We're looking at small things and then trying to make things, trying to get inspiration from them. Okay, and nanostructures present in nature, and what do we have done with them? Okay, um, so there's three things that we want to keep in mind. Biomimetic materials, artificial synthesized. That means that really we are not making things the way nature does it. We're just making them in a laboratory with different techniques. Okay, nanoscale is the base of the design. We really want to start from 0 uh, and get it to 100 or more. Okay, but we really want to get started from a nanoscale, from a very small scale. Or we can also do it. We can also start from a very big scale and then just cut it, chop it, slice it, and then get to nanoscale. And that can be done with some of our instruments. Natural systems can be modified, but this is not our focus of this paper, okay? So now let's talk about this. We are going to talk about the techniques that I already talked about to visualize this. One is scanning tunneling microscope, and the other is atomic force microscope. And in scanning tunneling, you have a sample and then some type of detector, and the detector uses electricity to scan the sample. And the other one, we have a atomic force microscope. And this one, you have a sample right here, and then you have a type of metal. It's called cantilever. And this metal is just, think about this as the metal. As the metal, well, we can use this as a metal. As the metal approaches a sample, it's going to be vibrating. If there's a bump, it's going to vibrate faster, right? Because it's a bump. So the smoother it is, it's not vibrating, but if it finds something, it'll vibrate faster. And then you have light on top, hitting it, light, right? And then we're gonna detect how much movement it has, okay? That's the way it works. Like I already explained, we use to make things, we use top down and bottom up approaches. So top down, starting from 0 up to 100 or more, or uh, from top down, starting from a big one and going down, or from bottom up, starting from 0 and going up. Now, we're going to talk about this, which is a type of biomimetic inspired nanomaterials and synthesis. The Lotus effect, if you haven't seen my video, please watch it. If not, I'll explain right now. So the Lotus is just a type of leaf, a type of plant that doesn't get wet. How does it do it? It has two ways. One is a contact angle and roll-off angle. These are ways in which this is a droplet of water. This is a surface of anything. It could be the Lotus leaf. And as you can see right here, there's a droplet is nicely formed. This angle, this surface right here is 180, right? 180. So we start the measurement from here, okay? From here to here, you see the space is very small. So that means that it would be from here to here, it would be like, let's say 150, and this would be like 30. So we really want theta, this angle, to be really high. That means that we have a very nice droplet. Okay, if it's low, the lower it is, the lower it is, lower it is, the more wet it gets. Okay. Now we can talk about okay, this one. It's called the roll-off angle. We really want this to be very small. If we have a drop on top of this, we really don't want to do this with a very high angle to make the drop leave, right, or roll off. We really want a very small angle so the drop roll off, okay? And that means that it's going to be very efficient system. This would be okay. And then over here we can see this is there's two types. One is called homogeneous wetting, where really water just gets everywhere inside in between. And we have heterogeneous wetting, where there's some type of air or other type of substance, and then the liquid is just floats on top. That would be called heterogeneous. Nature uses this model. It likes using this model right here because it's easier to get rid of the water on top. That maybe has a type of oil or liquid inside here. Who knows what it is, but it works. And now let's come over here. This is what the lotus leaf look like. It contains, they call it a double nanostructure pillar. Pillar is just some type of structure, such as the Romans, they used to reinforce things. And the way it does it is, you can see they have the mountain-like, it would be one lotus or pillar, one pillar, and then the other one would be a second pillar. So this would be one pillar, and then the surface outside would be the next pillar, or a lot of different pillars, a lot of them, okay? And so how do researchers make this? Okay, let's say we want to make that material. We want to make a super hydrophobic a material that it looks like the leaf. The way they do it is they really use a leaf itself. They use a leaf and then they put some substance on top. Let me use my pen. Okay, so they use a leaf and then they use a substance on top, right? And then they put some anti-stick layer. I'm not sure what this is made out of, but they put that. And then they peel it off. They peel it off, and then they get this. it would be called the negative template, which is this one right here on top. And then they put again the same substance, or you can use a different substance, but you can put the same on top of your negative template, which you already have. And then the end result is going to be this. It's going to be something, the replica, it's going to be something that looks like the lotus leaf, okay? So that's pretty clever. That's the way nature, that's the way we do it. All right, let's keep going. So why aren't they really in the market everywhere if we're really good at making them and it's easy to make them? Because they are short-lived. They get deteriorate and they could deteriorate and they get bacterial contamination. So bacteria are everywhere. They like to be everywhere, okay? And we haven't found a solution so far. I haven't come up with a solution yet, but I do have a solution from lab to the market. That's the important part. The way we can do it is we can just have a lot of replicas, right? A lot of replicas on top of each other. Maybe that would work and that would help with deterioration. Um, let me know if you like my idea, and if you have other ideas, also let me know. I will read the comments, okay? Now, to be continued for next videos, for next topics, we're going to talk about gecko feet, how they climb. Uh, the reason for that is they have very nice adhesive forces in their fingers. Self-healing materials. When we get cut off, we have wound healing, and nature also knows how to do that. It heals itself or herself, or however you want to call it. Also moth eyes. We have all seen this nice eyes on houseflies or moth eyes or other insects where they have a lot of eyes in their eyes, and we really want to study what's going on and why are they hexagonal, a lot of hexagonal structures. We're going to look at butterfly wings, how they are able to have very nice colors. Is it a product of they really have a lot of different colors, or they only use their body, their structures to make us to make it appear that they have a different color? The second one is true. And we're going to look at frog toe pads. Some frogs are also able to climb, just like the gecko. And we're going to look at some future applications for biomimetics, okay? I love you guys, and thank you for watching this. Bye-bye now, okay?